So here we have a definition of some collection of vectors. S is the set of all vectors A, B, C in R3 such that A times B is less than or equal to 10. In other words, all 3x1 vectors such that the first and second coordinates have a product that's no larger than 10. And to get a handle on, like an intuition for what this vector set is, what vectors are in this, I find it's often a good idea to just start listing out some examples of vectors that are members of the set and vectors that aren't members of the set. So can you tell me an example of a vector that matches this restriction?
An example can be 5, 2, 1.
Yeah. If we examine this vector, 5 times 2 is less than or equal to 10. So this vector is a member of set S. What would be a couple more examples of members of set S?
Uh, 3, 3, 3.
Yeah, 3, 3, 3. Because if you look at the top two coordinates, 3 times 3 is less than or equal to 10. So this is a member of set S. What would be some examples of vectors that are not members of set S?
Three, 4, 5.
Yeah, 3, 4, 5. Again, checking the first and second coordinates, their product is 12, which is not less than or equal to 10. So this is not a member of set S. And yeah, 10, 2, 4 would be another counterexample. Here's a vector whose top two coordinates have a product that is not less than or equal to 10. So this is not a member of set S. So it looks like we've at least got a general beginning of some vectors that are members of set S, some vectors that are not members of set S. One other thing to check, if this is going to count as a vector space, what's one vector that has to be a member of every vector space?
0 vector.
Yeah, the 0 vector. So if we want to know, is this a vector space? Before we even check any of the closure properties, it's a good idea to check the 0 vector. Because if the 0 vector is not in the set, then you know it's not a vector space. So does the 0 vector count as being a member of this set? Does it have this property? Yeah, it looks like it. The top two coordinates product, 0 times 0, is indeed less than or equal to 10. So yes, the 0 vector is part of this set. This set includes the 0 vector. Does that mean it counts as a vector space? No, because we still need to check what are the properties.
Adding and doing a scalar multiple.
Yeah, we want to check the closure properties, closure under addition and closure under scalar multiplication. So knowing that it includes the 0 vector doesn't really tell us anything. If it did not include the 0 vector, we'd be done. We'd immediately know it's not a vector space, and that's that. But containing the 0 vector, we don't know if that's enough. We still need to check closure. And to check closure under addition and closure under scalar multiplication, actually, let's go back to those vectors we just had. Shoot, what were they? Or it doesn't have to be those same vectors. What are some examples of a couple of vectors that are members of this set? Sure, maybe 2, 2, 2. And what's another example of a member of this set? 1, 1, 1. So this is a member of the set. 2 times 2 is less than or equal to 10. So is this. 1 times 1 is less than or equal to 10. If we add those, 3, 3, 3, is that also a member of the set? So it looks like we've just taken a vector in S plus another vector in S, and the result is also a member of S. Does that mean S is closed under addition? No, because this is just one example, right? One example doesn't show it's true for everything. Because closure under addition is a universal claim. It's a claim that for any two vectors in S, this property has to hold. So just showing one example doesn't prove it. If we wanted to prove it, we'd have to do this with variables. We'd have to say, let's say ABC plus XYZ would be A plus X, B plus Y, C plus Z. And the only thing we would know is that AB is less than or equal to 10 and XY is less than or equal to 10. And we'd want to show that A plus X times B plus Y must be less than or equal to 10 if we wanted to prove closure under addition. However, is this set actually closed under addition? Doesn't really look like it. Because closure under addition would mean if you take two numbers that multiply to something less than 10 and two other numbers whose product is something less than 10 and add those, you can guarantee that the new product is still less than or equal to 10. And I don't think that's the case. Can you come up with a counterexample to that? Can you come up with two vectors that match the condition, but whose sum does not match the condition?
Could do 333 and 520.
Yeah, let's try that. Because 3 times 3 is less than or equal to 10, and 5 times 2 is less than or equal to 10. So these are both members of S. But if we add them up, the product of these numbers, 8 times 5, is not less than or equal to 10. So the result is not a member of S. That breaks closure under addition. We can now say this set is not closed under addition because we found a counterexample. We found two vectors that are members of the set, but we added them together and the result is not a member of the set. One counterexample is enough to disprove a universal claim. So we can say this is not closed under addition, so we know for sure this is not a vector space. We could also check closure under scalar multiplication, but whether that's true or not, violating one or the other of them automatically means this is not a vector space. Any questions on that so far?
I have a question.
Mhm.
So for this, if I do, can I write down on the side like A times B is less than or equal to 10 and X times Y is less than or equal to 10? Does that make sense to say that?
And like in this case,
Yeah.
yeah, we'd say we would say we assume
Mhm.
that AB is less than or equal to 10, and also XY is less than or equal to 10.
Okay.
In the sense that we are assuming that these are both members of set S, and that's what being a member of set S means. And then if we tried multiplying out A plus X times B plus Y, we get AB plus AY plus BX plus XY. And we do know that AB is less than or equal to 10. And we do know that XY is less than or equal to 10. But we don't know anything about AY and BX. Those could be anything. And also, just because even ignoring AY and BX, if we just have AB is smaller than 10 and XY is smaller than 10, their sum might be larger than 10. So this tells us we can't guarantee that the sum is going to be a member of S. It doesn't, there's no reason to expect it to follow that property. Likewise, if we tried scalar multiplication, if we take A, B, C such that AB is less than or equal to 10 and multiply it by some real number R, we get RA, RB, RC. Would we expect that RA times RB must also be less than or equal to 10? Can you come up with a reason why that should be true? Or can you come up with a counterexample that shows it must be false? Or at least can be false?
If we multiply it by 30, it'll be false.
Yeah, like if you take this vector 333, multiply by 30, you get 90, 90, 90, and 90 times 90 is definitely not less than or equal to 10. Yeah, as long as, in fact, no matter what ABC is, even if A and B are very, very small, as long as they're not 0 and 0, 0 or 0, if you multiply it by a big enough number, you're going to scale that vector up so that it's no longer a member of set S. In fact, in general, any definition of some set of vectors where the condition is some restriction on the size of the vector, those generally are not vector spaces. Because anything that's got some restrictions on the size of the vector, you could always make the vector a different size using a scalar multiplier. So anything involving a restriction on the size is probably not going to be a vector space. And you can generally disprove that by saying, well, what if we multiply it by a really big number? Or what if we multiply it by a really small number? In fact, if the restriction is that the size must be greater than some amount, you can immediately prove that's not a vector space by showing that the zero vector is not included. For instance, if the restriction is all vectors whose magnitude is greater than 2, that automatically excludes the zero vector, so it's not a vector space. Or if you wanted to prove closure or disprove closure under multiplication, you can just say, suppose you got a vector whose magnitude is exactly 2. Take half of that. That's no longer magnitude 2 or greater. So any set of vectors that has some restriction on size is very probably not going to be a vector space. And usually the way you would prove that is by showing it's not closed under scalar multiplication. Any other questions on that so far? Or any other examples you'd like to try out? Then let's take a look at the idea of the column space. Let me make up an example matrix we could use here. Yeah, let's say this is our matrix. So 1, 2, 6, 1, 1, 1, 1, 4, 1, 0, 3, 2, 10, 1, 1, 1, 2, 6, 1, 1. With this matrix, if we want to find the column space, first of all, what does column space mean?
It's the span of all of columns.
Yeah, the span of all the columns of A. In other words, all possible results that you can build by making linear combinations of these 5 columns. And also another very useful way to think of that, if you multiply this matrix times some vector, what does A actually get multiplied by? And what does B actually get multiplied by? And so on.
A is multiplied by column 1, B is by column 2.
Yeah, each one of these numbers gets multiplied by an entire column. As you combine row and column, you get something from the first column times A, something from the first column times A, something from the first column times A, and then B, C, D, and E times the other columns. But overall, this gives you A times the entire first column, plus B times the entire second column, plus C times the entire third column, and so on. So this is a very useful way of thinking about the column space, because this is just a linear combination of the columns. So another way to write the column space, this isn't really the definition, but it's a direct result of the definition, that the column space also equals the set of all results of A times X, such that X could be any vector in R, in this case, R5. More generally, R to the n, where n is the width of the matrix. So this is a very useful way of thinking about column space, often even more useful than the definition itself, that the column space of a matrix is the set of all possible outputs, all possible results of multiplying A times a vector. In fact, if you think of A as a function and X as the input vector, the column space of A is just a set of all possible outputs of that function. If you think of this as A times an input vector equals an output vector. And you think of A as a function that turns an input vector into an output vector. AX, or sorry, the column space of A just means all possible results, all possible outputs, no matter what the input is. So this is in many ways very much like the range of a function. We're just listing out all possible outputs, all possible results of A times anything. So that's probably, I would say in many cases, the most useful way of thinking about a column space. But keep in mind the actual definition is the span of the columns. That is all possible linear combinations of the columns of A, some or all of the columns. Any questions on that so far? And ultimately, the reason we can call it a column space, the reason we call it a vector space in the first place, is because if you take any linear combination of the columns and add it to any other linear combination of the columns, the result is just another linear combination of the columns. So the column space is closed under addition. Or if you take any linear combination of the columns and multiply it by some scalar, every one of these coefficients gets multiplied by that scalar, but it's still just a bunch of coefficients times the columns of A. So any scalar multiple of a linear combination of columns is another linear combination of columns. So the column space is closed under scalar multiplication. Those two closure properties are why we can call it a column space instead of just a column set, that it really is a vector space. However, although we define the column space as the span of all the columns, we don't really need all of the columns. There's some redundancy here. And there's not always redundancy, but in this case, we can tell we don't really need all 5 columns, because what set is the column space a member of? What universe does this column space exist in? This column space here is a subset of what universe? That is, what larger vector space is this column space part of? If you consider all these columns, these are all 4x1 vectors, right? What do we call the set of all 4x1 vectors with real numbers?
R4?
Yeah. So we would describe this as the column space is a subset of R4. That is, everything in the column space is a member of R4 anyway. And more specifically, we would say the column space is a subspace of R4 in the sense that the column space is contained within R4, but R4 is a vector space and the column space itself also counts as a vector space. So the column space is a subspace of R4 in the sense that it's contained within this larger vector space universe R4. And also the column space itself counts as a vector space. And that means, since it's a member of a 4-dimensional universe, we shouldn't need more than 4 vectors to span it. So we don't need all 5 of these. We need at most 4. We might not even need 4 of them, depending on whether the column space is the entire universe or not. But we can tell from the fact that this is in R4, at least one of these vectors is redundant and can be eliminated without changing the information. So what we want to do is we want to get rid of the duplicate information. We want to trim this down to only the information we absolutely need. And we can do that, as usual, by using row reduction. So let's try row reducing this, so we can figure out where the redundancy is. Because we know at least one of these columns isn't really needed. Row reduction can help us figure out what information we do need. So how would you row reduce this? What would be a good first step towards getting this into, or getting rid of the extra information?
I multiply the first row by -1 and add it to row 2.
Yeah, we'll modify row 2 by adding -1 times row 1. And let's see what that turns into. First row, we're keeping the same. Second row, we're subtracting the first row. So 1 minus 1, 1 minus 2, 4 minus 6, 1 minus 1, 0 minus 1. And then while we're at it, we may as well also modify the third and fourth rows. We want to get rid of this 3. So we will add -3 times row 1. And what do we get there? What would our new row 3 look like if we do that operation?
It'll be 0.
Mhm.
And then -3. So 6 plus 2.
We've got a -6 though, and we're adding
Oh,
the 2.
oops. -6 plus 2, -4.
Mhm. And then 10 plus -3 times 6.
Arithmetic, not too good.
10, -3 times 6 would be -18. So 10 minus 18 would be -8. Since the 10s cancel out, we still have a -8. And then 1 minus 3, 1 minus 3 again. So that's our new second row, or sorry, new third row. And also, what about the fourth row? What could we do with that?
Subtract it from the first row.
Yeah. Or rather, subtract the first row from the fourth row. In fact, since the first and fourth rows are identical, what's going to happen to the fourth row?
All zeros.
Yeah. We get a row of all zeros. And that's important in its own right. That tells us that the fourth row was just duplicating information we already had, which we can see visually from the fact that it's exactly the same as the first row. But that also tells us if we're trying to find the row space, we would ignore the fourth row because the fourth row doesn't provide any new information. And let's tidy this up a little bit also. I noticed, for instance, we've got a -1 here. We probably want to turn that -1 into a +1 to get the new pivot. So let's multiply that by -1. And also, what are all these values multiples of?
2.
Yeah, so let's divide by 2 to get them all to easier numbers to work with. In fact, let's divide by -2, so the pivot is going to be positive. So multiply by -1/2. And this is not really a necessary step, but it tidies up the numbers and is going to make the next steps easier, I think. So we've got first row unchanged. Second row, we're just multiplying by -1. Third row, we're multiplying by -1/2. And fourth row is still all zeros. And at this point, if we take a look at the restrictions for reduced row echelon form, if we look for the pivots, this pivot is a 1 and alone in its column. This next pivot is also a 1, but it's not alone in its column yet. So what would we need to do?
The number and above and below should be 0.
Yeah, we want to turn this number into this 2 into a 0. So let's add -2 times row 2. We also want to turn this 2 into a 0. So let's modify row 3 by adding -2 times row 2 as well. And then row 4 is already all zeros, so we can just leave that as it is. So we've got 1 minus 2 times 0, still 1. 2 minus 2 times 1 cancels out. 6 minus 4. 1 minus nothing. And 1 minus 2. And then second row, we're not changing at all. So that's still 0, 1, 2, 0, 1. Third row, we are changing. 0 minus 0, still 0. 2 minus 2 is now 0. 4 minus 2 times 2. So that's 4 minus 4. That's also 0. 1 minus nothing is still 1. And then 1 minus 2 is -1. And then fourth row, still all zeros. Is this now in reduced row echelon form? Not quite, because this first row has a pivot that's a 1 and alone in its column. The second row has a pivot that's a 1 and alone in its column. But what's wrong with the next pivot?
There's a number above it.
Yeah, it's not alone in its column. It's got this non-zero number above it. This is actually enough information at this point. If we stop at this point and we say we now know where the pivots are, if all you care about is the column space, knowing where the pivots are is enough information. But let's take this one more step, because fully row reducing it does give you useful information for finding other subspaces. So let's go ahead and subtract row 3 from row 1. And that should finish it off all the way to reduced row echelon form. 1 minus nothing, nothing minus nothing, 2 minus nothing, 1 minus 1, -1 minus -1, and then the other row is unchanged. So this is now reduced row echelon form. And we can now use this to get some very useful information. First of all, just identifying the pivots, first non-zero in each column, first non-zero in each row as you read from left to right. And then the fourth row is all zeros, so it has no pivot. This matrix has 3 pivots. And what do we generally call the number of pivots in a matrix? Have you seen the terminology for that yet?
The rank.
Yeah, we would say the rank of matrix A is 3 because it has 3 pivots. And that essentially tells you how much unique information the rows and columns have. That we had 5 columns, but only 3 of them are really important. The others are just duplicating information the others had. We have 4 rows, but only 3 of those rows are really important. The 4th one was just duplicating information the others already had, which is why it's able to cancel out. And we can use those pivots to write out a basis for the row space and the column space. Earlier, we said that the column space could be written as the span of the 5 columns, but it turns out we don't need all 5 columns. We knew we wouldn't need all 5. We knew we would need at most 4, but it turns out we actually only need 3 because there's only 3 pivots. This matrix is only rank 3. We can't use these final columns though. We can't use 1 0 0 0 0 1 0 0 and 0 0 1 0 because we weren't doing column operations. We were doing row operations. If you add a row to another row, you're preserving information about the row space, but you're scrambling up the columns. So we can't use the final columns, but we can use their position. We have the first column, the second column, and the 4th column. So the first, second, and 4th columns are the pivot columns. These are the columns where the pivots exist. So we would look for the first, second, and 4th columns of the original matrix. And then we would say that the column space of A can be written as the span of just those 3 columns. We don't need to list out all 5 columns, just the ones that actually provide unique information. So the column space is in R4. It's part of a 4-dimensional universe, but the column space is only a 3-dimensional subspace of that 4-dimensional universe because we only need 3 columns to span the whole thing. And that means that the 3rd and 5th columns are not actually providing unique information. The 3rd and 5th columns in some way can be written as linear combinations of the 1st, 2nd, and 4th columns. In particular, I think we can say, if we take 2 times this plus 2 times this, like 2 times 1 plus 2 times 2 is 6, 2 times 1 plus 2 times 1 is 4, 2 times 3 plus 2 times 2 is 10, 2 times 1 plus 2 times 2 is 6. So the 3rd column is actually just 2 times the 1st column plus 2 times the 2nd column. And likewise, the fifth column can also be written as some combination of the first, second, and fourth columns, or possibly just one or two of them. But in general, this means that the third and fifth columns are not necessary. They're just duplicating the information that the first, second, and fourth columns already provide. So we would just say that the column space is the span of these three vectors, and we would say these three vectors are a basis for the column space. Basis meaning a set of vectors that are enough to span the set and also are linearly independent. So if he had written out all five, that would be more than enough to span the space, but they wouldn't be linearly independent because row or column 3 and column 5 are duplicating information that columns 1, 2, and 4 already have. For a basis, we want a set of vectors that's enough to span the set, enough to span the space, but just barely enough. So we require linear independence to eliminate the redundancy. And because we only need three vectors to span the column space, that is the basis for this space is three vectors, we would say that the column space is three-dimensional. Dimension of the column space is 3, which is also the same as the rank. Any other questions on the column space so far? As for the row space is all possible linear combinations of the rows. But we already found out we don't need all the rows. What rows do we actually need here? Or what rows can be ignored?
Row 4.
Yeah. Row 4 can be ignored. And in this case, you may be able to see that right from the start, from the fact that row 4 is just a duplicate of row 1. We don't need to list it twice. But even if it wasn't a duplicate, even if it wasn't obvious from the start, we could still figure it out from the row reduction. The fact that the final row cancels out to all zeros tells us that the final row wasn't really necessary. So we could say that the row space, instead of saying the row space is the span of all 4 rows, we could say it's the span of just the first 3 rows. Or perhaps more usefully, we actually could use the rows of the final result here. Because how do we get these rows in the first place? How do we get 10200, 01201, and 001 negative 1? How do we get those final rows?
Row operations.
Yeah, all of these were obtained from row operations using the original rows and derivatives of them using more row operations. So since these are all built from the original rows, these 3 final rows are also members of the row space. And they're enough to span the row space. We've gotten rid of all the redundancy. So the row space is a span of just these 3 rows. You can also write it as the span of the 3 original top rows, but it's going to be a lot easier to use these rows because all the 1s and 0s will make them easier to work with. So I would say the row space is the span of these 3 rows. In other words, we can use these 3 rows as a basis for the row space. And we often write them as columns anyway, like 10200. We would often write as a column. And sometimes we put a little T, a transpose symbol, to say this should really be a row. We're just writing it as a column. And likewise, 01201, transpose, and 0001 negative 1, transpose. So these 3 vectors are a basis for the row space. And note that these are members of R5 because these are 5 by 1 vectors. So we'd say the column space is a 3-dimensional subspace of a 4-dimensional universe. The row space is a different 3-dimensional subspace of a different 5-dimensional universe. It's a subspace of R5. So the column space and the row space don't really have anything in common other than they're both 3-dimensional. But they're members of different universes. Column space is a member of the R4 universe. Row space is a subspace of the R5 universe. The only thing they really have in common is their dimension, because they both have dimension equal to the rank of the matrix. You can see the rank is the dimension of the row space, and the rank is the dimension of the column space, and the rank is the number of pivots in the row reduced form. Those will all be the same number every time. Any other questions on that so far? And also, while we're at it, we could also find what's another important subspace related to a matrix we could find by row reducing. The row space, the column space, and what else?
Null space?
Yeah, the null space. Without doing any extra, well, a little tiny bit of extra work, using all of these row operation steps we've already done, we can use this finished product, the final reduced row echelon form, to very quickly find a basis for the null space. Because what does the null space mean? That's the set of all vectors that have what property?
When you multiply it by a matrix, it equals 0.
Yeah, exactly. The null space of a matrix, sometimes written as n of A or sometimes actually written out null of A. Either way, equals the set of all x in Rn such that Ax equals the 0 vector. In other words, all solutions to this equation Ax equals 0. And typically we would solve that equation by setting up an augmented matrix. And then row reducing. However, we already did all the row reduction we need on the coefficients. If we apply those same operations to all these zeros, what happens to all these zeros if you do row operations?
It'll still be 0.
Right, those zeros don't change at all, which means we can just pretend those zeros were there all along. We can just pretend we had those zeros there the whole time. We just didn't bother writing them in. If these had been anything other than 0, if you were trying to solve Ax equals some other vector, then they wouldn't stay the same, and you would actually have to follow through each step, figure out what happens to these numbers. But with Ax equals 0, it's much more straightforward. Those zeros are just going to stay zeros, which means we can just go back to the final result, the final reduced row echelon form. Each one of these rows can now be rewritten as an equation. Let's say vector x is, let's just call this A, B, C, D, E for now. If we rewrite each of these rows as an equation, then we'll have a much simpler system of equations than the original. So for instance, first row, we have 1A plus 2C and no B, D, or E at all. So A plus 2C equals 0. Likewise, for the second row, we've got no A at all, but we've got 1B plus 2C plus 1E equals 0. And likewise, for the third row, becomes the equation 1D plus negative E equals 0. So with those three resulting equations, which are much simpler than the equations from the original matrix, we can now rewrite these by solving for certain variables. And typically what you want to do is solve for the pivot variables. We've got pivots in the A column, the B column, and the D column. So we'll want to solve one equation for A, one equation for B, and one equation for D. The advantage of using the pivots is that each pivot shows up in only one row. This is really the reason why we want the pivots to be isolated in their column, so that A, which is associated with this pivot, shows up only in that first equation and doesn't show up in the other equations. It makes the equations separable. Likewise, B shows up only in the second equation because this pivot has zeros above and below. It's alone in its column. So we could isolate, for instance, A, we could subtract 2C from both sides. B, we could subtract 2C and E. D, we could add E to both sides. And at this point, we could now write out our matrix, sorry, our vector, our solution vector A, B, C, D, E. But we can replace A with negative 2C. We can replace B with negative 2C minus E. C we would just leave as it is because it's a free variable. C could be anything. D we can replace with E, and E we would leave as it is. So we've taken our solution vector, which has 5 unknown variables, and rewritten it in terms of only 2 unknown variables. That simplifies things considerably. And also, we can now split this up into a vector that depends only on C and another vector that depends only on E. For instance, this negative 2C, I'm going to write as negative 2c plus 0e. Negative 2c minus e, that's negative 2c plus negative 1e. C is just 1c plus no e at all. E is 1e and no c at all, and then same e, 1e, no c. The advantage of doing that is that now each one of these vectors has only one variable, and it's a variable that shows up in every term, so we can factor that out. The first vector, we can write out c factored out, and then what's left is just the numbers. Negative 2, 1, 0, 0. Likewise, factor in e out of this vector. We're left with 0, -1, 0, 1, 1. In other words, our solution vector, the vector that could have been any vector in the null space, can always be written as a linear combination of -2, -2, 1, 0, 0, and 0, -1, 0, 1, 1. In other words, we've just found a basis. These two vectors, without the c, without the e, just -2, -2, 1, 0, 0, and 0, -1, 0, 1, 1, those two vectors are a basis for the null space, because every vector in the null space can be written as a linear combination of them, and they're linearly independent. Which means, what's the dimensionality of the null space? How many dimensions is the null space here?
2.
Yeah, it's a two-dimensional null space. The dimension of the null space is 2. And we also write that as the nullity of the matrix. The nullity of matrix A, that just means the dimension of the null space, is 2. The nullity is 2 because we had two free variables, each free variable being associated with one solution or one direction of solution. And why do we have exactly two free variables here? Where did that 2 come from? Why C and E specifically?
Those are the ones with no pivot.
Right, we had two columns without pivots. Those two columns represent free variables. And since we have two free variables, the null space is two-dimensional. And so you can always tell what the nullity and rank are as soon as you get to reduced row echelon form, or even before that, as soon as you know how many pivots there are, even if you haven't fully row reduced. As soon as you know how many pivots, the number of columns with pivots tells you the rank. That's the dimension of the row space and the null space. And the number of columns without pivots tells you the dimension of the null space, since that's the number of free variables. And what do those have to add up to if we add together the rank plus the nullity? That is, if you add together the number of columns with pivots plus the number of columns without pivots, what do you get?
The number of columns.
Exactly. We're taking the 3 columns with pivots, that's the rank, plus the 2 columns without pivots, that's the nullity. That just adds up to the number of columns. This is usually called the rank nullity theorem, that the rank plus the nullity always adds up to the number of columns of the matrix, because it's just adding up the columns with pivots plus the columns without pivots to get the total number of columns. Rank nullity theorem. Any other questions on that? All right, then I'd recommend to get some more practice. Try this out on your own with another matrix. You can really choose any matrix you want. Try row reducing it all the way to reduced row echelon form. And once you've got it in reduced row echelon form, you can use that to write out the basis of the row space, the basis of the column space, and a basis for the null space all in one go, just from that one row reduction. So give that a try. Let me know if you have any other questions, and I will see you next time.